Good morning, everybody. Welcome to the Simons Institute for the workshop on extroverted algorithms. My name is Sampath Kannan. I am the associate director here. For most of you know me, but introducing myself to the others. And a brief word about the Simons. Everyone probably here knows that too. But the Simons was founded by a generous Simons Institute was founded by a generous grant from the Simons Foundation in 2012. And we are going strong, and we see ourselves going strong for at least another 10 years. And we shall see what happens after that. The Simons brings together, people working on core theoretical questions, thinking about what computation is and what resource constraints you can deal with, and so on. But it also is concerned with looking at the rest of the sciences and society through an algorithmic lens. And there are many programs and workshops here that actually, connect computer science, or theoretical computer science, to neuroscience, economics, physics very strongly, biology, all kinds of fields. So we really like that role as well, extending the reach of theoretical computer science to other disciplines. So a few sort of housekeeping announcements. First of all, we do not allow any food or drink, not even coffee, in this auditorium. So please remember that. If you brought in a coffee this time, you're forgiven for a little while, but next time, please don't do that. And the other thing is that the staff here are very busy because there's a series of 10 weeks of nonstop workshops between various programs and standalone workshops. And so we would like to make sure that they get to go home at 5 o'clock when the day finishes. So one thing that means is that if you want to have lingering discussions after the workshop, please have them outside, because they will want to lock up the auditorium and leave. So don't hang around the auditorium and prevent them from doing that. So that's the one other request. And I look forward to a great workshop here. I'm handing off to Graham, who will introduce the workshop.
Wonderful. Thank you so much. So yes, welcome everyone to this workshop on extroverted sublinear algorithms. Many people, when they first hear that description, look a bit puzzled and say, well, what do you know, I understand. Obviously, we all know what algorithms are. Sublinear, well, a school child knows what sublinear means in the context of algorithms, but what does extroverted mean? And of course, the answer is that by the end of this week, we will certainly know. So over the course of this week, we have a collection of great talks. We have tried to structure the timetable so there's time in between those talks to converse, discuss, start collaborations. On each day, there is something special to look forward to at the end of proceedings. So today we have a reception at the end of the afternoon. Tomorrow we have a panel thinking about the interaction of algorithms and industry. Wednesday, of course, is a public holiday, and we'll be crowdsourcing ideas of things that people might want to do, some suggestions that they may be wanting to do hikes or go and explore San Francisco. On Thursday, we'll have the open problems session, so start thinking now about which open problems you would like to share. And on Friday, we have the lightning talk session at closing the proceedings. So that's the opportunity for people to give a short talk on anything relevant to the topics of the workshop. So please, don't be discouraged. Please think now about whether you can either have something that you can summarize in 5 to 10 minutes, or even think of something new over the next day or so. So if you would like to give a lightning talk on Friday, please send an email to Sepide, who will collect those volunteers, and we'll come up and we'll figure out the program by Friday. Last, again, everyone is welcome here. Please interact within the workshop. There are some people who've been working on sublinear algorithms for a while, some people who are still getting into it, but we're all participants at this workshop. So please, just come up, talk to people. We'll try and arrange people to hang out at lunch so you can create connections and interact with new folks. And generally, let's make this a very collaborative and enjoyable week. So we now get to the first session, and I'm delighted to introduce Jelani. Jelani is a local from Berkeley itself, who's worked on just a wide number of problems around sublinear algorithms. And he's going to talk to us today about one of the most fundamental problems that we thought we knew how to do, but he's going to tell us actually there's even more to learn about something as foundational as counting. So Jelani, please take it from here.
Okay, thanks for the intro. I'm going to talk about a couple joint works, one with joint with Huacheng Yu, and another one joint with Ishaq, Yanjun, and Huacheng, related to approximate counting. So the problem that we're going to discuss most of this talk is this. It's a data structural problem. We have to maintain a counter n subject to 3 operations. Initialize sets it to 0, increment adds 1, and query just returns the value of the counter. Sounds simple enough. And the goal is to use as little memory as possible, which will measure in bits. And there's a straightforward solution. You just maintain the counter in memory. It takes log n bits. And the question is, can you do better? And the answer is clearly no. If you formulate it the most natural way, if you say, for example, I promise you that the counter has value between 1 and t. Now I want to use less than log t bits. Well, pigeonhole principle says you cannot do better than log t. Otherwise, 2 different values would have the same memory footprint, and you'd get at least one of them wrong. But if you relax the problem a little bit, then the answer becomes yes. And the first algorithm that did this is the Morris algorithm. So this is Rob Morris, who was at the NSA for a while, although he developed the algorithm not for the purposes of, well, as far as we know, not for the purposes of intelligence, but for actually a spell checker in a program called Typo for Unix in the 70s. Also father of, I always find this funny, like the head of security of our country's son was the creator of the first internet worm, but now he's I guess cleaned up his act. So why do we want to do better? Isn't log n already pretty small? So the original motivation, which is what I mentioned from this spell checker, I found in this, well, it's in the paper itself, and there's more information in this article, survey article by Lombroso, The Story of Hyperlog. Hyperlog is a different algorithm for distinct element counting, but he talks about Morris's counter as well. So he says, Rob Morris wanted to count the occurrences of trigrams in texts. Right? Trigrams are sequences of 3 characters. So if there are, let's say, 26 letters, there are 26 cubed trigrams. And he was using these counts to feed into Typo, which was some statistic-based spell checker in early Unix. And I guess the point was, if you had 26 cubed counters to maintain, and you looked at the machines that Rob Morris had access to in the 70s, he could only afford something like 8 bits per counter. And 8 bits just wasn't enough to store the counters. Like some of them were getting bigger than that. So there it says, 26 cubed 8-bit counter. So he needed some way of getting around this. So he developed an approximate counter, which is the motivation for the problem we're studying today. And it's a randomized approximate algorithm. So just to give you a visual, I implemented Morris's counter and ran an experiment. So what you're seeing here might look like a curve, but it's not. It's 5,000 blue dots. So you can tell toward the end that they're actually just discrete dots. So I ran his algorithm 5,000 times and just looked at what was the error profile like. Okay. So I gave the algorithm 8 bits. 8 bits should only be able to count up to 255. But I had the algorithm count up to a number that was about 100,000. Okay. So 100,000 is, I don't know, 17 bits, 16 bits, something like that. Okay, and it did pretty good. So what you're seeing is the empirical CDF, okay, of the error as a percent. So this is the median error over 5,000 runs. The median error was about 8% error or something like that. Over all 5,000 runs, the error was never bigger than 50% or so, right? So I mean, it's doing a pretty good job, and it's like saving half the memory and giving you still a pretty decent error. Okay. And the current motivation, and I shouldn't put question mark. Actually, so the current motivation is basically the same. You can say like log n bits is not a lot, right? But the point is the places where people use Morris are applications where you don't just have one counter, but you have a million counters. You have a lot of counters, right? So then the space per counter, even though it's a small number, is multiplying a big number. So I want that multiplier to be small, okay? So for example, I didn't put it here, there's an in-memory database called Redis. It's, I think, the most popular in-memory database that's being used these days. And a lot of people use it as a cache. And when you have a cache, you need a cache replacement policy. And we, as theorists, might snub our noses, but one of the ones they have implemented there is least frequently used, which is not competitive, okay? But it's there. And if you look at the implementation of least frequently used, it's like, well, every page in the memory needs to keep a count of how many times you accessed it. That's a counter. They use the Morris counter. Okay, so that's like one real world example of people actually using the Morris counter in the wild. Okay. There are some also applications in theory land where if you have a Morris counter, you can have an approximate counter, you can use it for something else. One of them, for example, I'll just say the bottom, is people might have heard of moment estimation in data streams, estimating the LP moments, like the AMS, Alon Matis and Segedi paper, which was one of the foundational papers in streaming. So if you want a 1 plus epsilon approximation to say the LP norm for p less than 2, it's known from index work, which, and before that for L2 from the AMS sketch, that you can do 1 over epsilon squared times log n bits of memory, where n is the domain size. But the lower bound for insertion only is not 1 over epsilon squared times log n, it's 1 over epsilon squared plus log n. And for p less than 1, we know that up to log factors, basically that's achievable. And that's Rajesh right there, thank you, okay. And that uses the Morris counter. As a subroutine, they use the approximate counting inside that algorithm. So as you can imagine, counting is a basic building block. I mean, counting is a very basic thing. If you have a better counter, you can probably do things with it, right? And you can, okay, so that's what this slide says. So first, I'm just show of hands, like who here does not know anything about how Morris algorithm works? Okay, oh, who here does? Okay, so most do, okay, so I apologize. So some of you don't know, so this will be new to some of you. And I think I'll still say something that if you don't know how our new result works, then you will learn something. Okay, so his first idea is to not store the actual counter in memory, but store a different value. Let's call it x initialized to 0. And this is not Morse's algorithm. We're getting there. But let's say whenever a user increments the counter, what I'll do is I'll flip a coin, and I'll only increment x if the coin is heads. Otherwise, I do nothing. And now, why does that do anything? What's the point of that? Well, we expect to increment x only half the time. So in expectation, x is only n over 2. So from x, we can derive n. N is 2 times x, right? So we can still estimate n, given only x. But we're storing a number that's only half as big. So we've saved a bit of memory, 1 bit. Okay, not a lot, but we've saved something. Oh, for some reason, okay, I don't know, it got cut off. But the downside here is that we're only saving 1 bit of storage. Okay, there's another downside, which is that if we want multiplicative error, if n is small, the error is going to be large. Like for example, let's say n is 1. There's been 1 increment. Okay, then x is definitely either 0 or 1, which means our answer will either be 0 or 2. So we'll be off by 100% either way. Okay, so this is bad for small n, and it also doesn't save us enough memory. I don't know why it's getting cut off, but hopefully that doesn't persist. So better storage. Let's hold off on fixing the approximation issue and just fix the storage issue for a second. So this is getting closer to what Morse does. Whenever a user increments n, you flip x coins, not 1 coin, and you increment x only if all the x coins are heads. In other words, you increment x with probability 2 to the minus x. And you can prove that in expectation, 2 to the x is n plus 1, which means we now have an unbiased estimator of n. 2 to the x minus 1 is an unbiased estimator, which means kind of if things are going according to expectation, you expect x to be about log n. And x is the thing you're storing in memory. So how many bits of memory does it take to store x? It takes log x bits, which is log n. So it takes log n bits of memory. OK. I had a proof written down, but I think I can skip that proof. How do you prove that This is an unbiased estimator. Let's skip that. But so this fixes the issue of we're only saving 1 bit of memory. Now we're actually saving a lot of memory. But unfortunately, this is still cut off. It doesn't fix the issue of approximation. Like I want a 1 plus epsilon approximation with 99% probability. This is not going to get you that as I've described it. So there's a usual technique that we're all familiar with in randomized algorithms, which is, look, I told you that this thing is an unbiased estimator. So if you want to reduce failure probability and get better approximation ratio, you do some kind of median of means or something, and instantiate multiple estimators and average them out. So that's a typical technique. How many estimators would you need to average? So it depends on the variance. Okay. And then you would set the failure probability to be a third, and you'd output the median of log 1 over delta of those, and then you'd get failure probability delta. And this, if you do the calculation of what the variance is, this would give you a final memory bound that looks like what I wrote there. Kind of 1 over epsilon squared log 1 over delta. That's the usual kind of thing that you see in these kinds of Chebyshev arguments, times the memory cost of a single counter, which is log n. Okay. And this turns out to be not good. This turns out to be wrong. Well, not wrong. I mean, it's correct. It's a correct analysis of this approach, but it's not the right way to do things for this problem. Okay. Here's a better approach, which Morris himself already knew, and Flageolet had a more refined analysis of it as well. But as you're going to see soon, I mean, there was something that was missed, and that's where Huacheng and I stepped in and tightened something. Okay, so this is not maybe how they described it in their papers, but this is how I'll describe it because to me at least, it kind of screams what you should do. Okay, so let's think for a second. On the one hand, I said you can increment with probability 2 to the minus x, which is 0.5 to the x. That gives you low memory. It's log n instead of log n. But the variance is something non-zero, and let's call that high variance. The other thing you can do is the trivial algorithm, which is just like maintain the counter. Don't use randomness at all. Just increment x every time you see an increment. Okay. Now there's no variance whatsoever, but the memory is high. It's exponentially worse. It's log n instead of log n. And if you just look at this, well, there's a natural question to ask, which is like, what happens, in between? Instead of 0.5 and 1.0, what if I make it 0.99? Okay. Well, if I increment with probability 0.99 to the x, you can still come up with something that's an unbiased estimator of n. Okay. And more generally, let's say I increment with probability 1 over 1 plus a to the x. Think of a as like 0.01. A is something very small. You can prove that this thing is an unbiased estimator of an plus 1. So in other words, if you subtract 1 and divide by a, it's an unbiased estimator of n. And you can also analyze the variance of this estimator. And the variance is something like a times n choose 2. Right? N choose 2 is a fixed thing. A is the thing that the parameter you're choosing. So you can slide a. Like I can decrease the variance by decreasing a, but then of course I expect it to increase the memory. Because if I make a 0, it's a deterministic counter, right? So there's some trade-off there, and let's try to understand the trade-off. If you set a to be this, I'm not going to do the calculation, but just take my word, 2 times epsilon squared delta, and then do a Chebyshev argument, basically everything will work out. Okay? And your memory will be that, log n plus log 1 over epsilon plus log 1 over delta. And I mean, more specifically, the memory is always going to be, you can show the memory itself is a random variable, by the way, right? Because it could happen that randomly you increment x every single time, and then you have high memory, but that's unlikely. But if you just look at the expected memory or the memory with high probability, the memory is very tightly concentrated around log n plus log 1 over a. So if you set a to be epsilon squared delta, you get the bound that I told you. Okay. So that's what was in Morris proposed this algorithm, Flageolet and analyzed it. Gronemeyer, Sauerhoff also had some later analysis as well. And it gets you this kind of bound. And the first contribution is that with Huacheng, we're able to show that actually the memory should be not log 1 over delta, but log 1 over delta. So we got a better upper bound and proved the matching lower bound. Okay, so even the lower bound wasn't known before. Yes. Oh, okay.
But why not have the probability variable, as in when the number is small, updated with high probability, and when the number is large, updated with a low probability? Would that make any sense at all?
You're saying change the probability of increment depending on the time.
Yes.
I don't.
You're already doing that automatically.
You are, because it is a function of x. You're incrementing with probability some f of x,
Yes.
like 1 over 1 plus a to the x. So I guess, yeah.
So is that the I mean, is there some flexibility there? Is there any reason to believe that is the
Correct probability of increment? Well, I guess you'll see very soon. Okay, when you see we're going to see very soon what is optimal.
Shall I ask a slightly different question?
Okay, okay.
Like in these applications, you probably have a fixed space.
Okay.
And you have to choose the parameters, right?
Sure.
So is there a way in which you, like, if I say, okay, you have, whatever, 256 bits to come, what should you set your parameters to get the best possible result? Is that?
Yeah. So I mean, so maybe I don't know if this will answer your question, but the point is, okay. Your memory is, for this algorithm, your memory is log n plus log 1 over a, right? So even though I'm describing the result as 2 parameters, there's epsilon and delta, in terms of parameterizing the algorithm only has 1 parameter, which is a.
Right.
So if you have some upper bound idea of what n could possibly, like, if you know that n is never bigger than blah, or log n is never bigger than blah, then whatever your memory available to you is basically forces your choice of a.
Maximize a according to that or something.
Or minimize a. Yeah, you could do that, for example. So it's like a 1 parameter choice. Does that address what you were asking?
Yeah, I'll come back to it.
Oh, okay.
But it does.
But this is just in expectation. So
The memory is very tightly concentrated around this value. But yes, it is. The memory is a random variable, and it could exceed that. And I guess, it's a randomized algorithm. So if you had some memory budget, and the memory your algorithm actually wanted for a particular run exceeded it, you could just say fail, because it's unlikely to happen anyway. Okay. So we showed 3 things. One is a new algorithm, but the algorithm is not that complicated, that has a simple analysis that shows that this log is actually achievable. And then we showed that the Morse counter itself actually, well, not exactly the Morse counter, but the Morse counter with like a 1-line change, okay, also achieves the same bound. And then we showed a matching lower bound against any algorithm. Okay. So the new algorithm, the item 1 here, so the basic idea is, first, let's not think of the original problem, let's think of a promise problem. In the promise problem, you're promised that either the final value of the counter is less than t is some threshold, or it's bigger than 1 plus alpha t, and you just need to decide which case you're in. Okay. So the solution is we're going to store a different counter y in memory, and we're going to increment that counter with this probability, log 1 over eta divided by alpha squared t. With this probability p. Okay. So what's the expectation? What's the expectation of the counter we're actually storing? It's p times n, and p times n is, if t is roughly n, then p times n, the t and the n roughly cancel. It's roughly log 1 over eta over alpha squared. Okay, so storing the counter in memory will take log pn bits, which is something like log 1 over eta plus log 1 over alpha, for example. And by Chernoff, we know that with probability 1 minus eta, the counter we're actually storing in memory will be concentrated. It will be 1 plus or minus alpha times pn. And notice also that once this counter we're storing gets too big, we can just stop remembering it, because we know that it's a fail. Like we know that we're in case 2. So in other words, the counter will never be bigger. Basically, I don't have to worry about the case where n does get too big. Pn will never be too big, because I'll stop storing pn at some point. So basically, the counter I store will I expect to never really be bigger than log 1 over 8 over alpha squared. So I can maintain it in log 1 over alpha plus log 1 over 8 of bits. Okay, so
Chopping off the tail or something like that. You're chopping off like the heavy tail in the original.
yeah, I mean, well, okay, when you say tail, I mean,
The problem is that because it's a randomized algorithm,
Yeah.
maybe the space could be too large, and what you're saying is once it exceeds the limit, just stop, and then there
Or
will
like
be
that,
expectation.
if it's not in the promise, no?
yeah, it's in the yeah. Basically, like I already know which side of the promise I'm in, so I don't have to waste memory for nothing. Oh, good.
So that's probably a dumb question, but shouldn't you pay a log t just to stop p or know when
P is like hard coded into the algorithm, I guess. It's not being yeah. Okay. I mean, also, you know, if you want to be, here's another way you could also think about it. Even if you did store P, you could round P to the nearest power of 2 to the minus K, right? And then store K. Okay, so storing P would actually take you log 1 over P bits or something like that.
Are there applications of this particular problem where you just came up with this as an approach to get to the final result?
I don't know. We just did this for this problem, for this particular application. Okay, so back to the original problem. Essentially, the original, to solve the original problem, you just solve multiple, instances of this problem in series, right? So like in the beginning, n starts off as 0, and you wait until it crosses some threshold, and then when it crosses the threshold, you then try to solve the next threshold, and then you just track it. So we'll track x such that with t being something like 1 plus epsilon to the x, okay, and we'll set alpha to be something like epsilon squared and eta to be delta over x squared, because we want to union bound and want some failure probabilities to converge or something. But oops. Okay, so when y hits 1 plus alpha over 2 times t, that's the upper limit of that threshold, then we'll reset y and we'll increment x. Okay, and the failure probability is at most the probability that we fail any of these sequential threshold problems. Each one has failure probability delta over x squared, so it's the sum overall values that x takes on of delta over x squared, which converges to O of delta. Also, every time we pass from one of these problems to the next, we have some kind of additive error that looks like alpha times t. Okay, so you add up all those errors that you accumulate from these sequential problems, and that also, because alpha was chosen in this way to be epsilon squared, right, which we can afford anyway because our memory's like log 1 over alpha, right? So epsilon squared and epsilon are basically the same thing in terms of memory. This memory converges to O of epsilon as well, or this error. Okay, and that's okay. So I guess there's something with my monitor that's not aligning properly. That's cutting off the bottom of everything. Let me very quickly try to fix that, and if I can't, then I'll give up.
So as the
Okay, that's better.
as your counter gets bigger, you're really resetting the probability to something smaller and updating the value as if you had used the smaller probability to begin with. That's what this.
That's right. That's true. That rescaling of p over p prime. That's right.
So it really is adapting to the probability as you go along. Maybe it's
This algorithm is, but so was the Morse counter, because it was also choosing the increment probability to be a function of x itself. And
so what's the difference? You're getting the probability is getting smaller faster. Or?
Okay. So you said what's the difference? Why is this better? Why is this worse? I mean, okay, maybe to. By the way, is this?
You're going to prove the same bound for them.
I will, and I'll do even more than that. You'll see in a second. But just one question: after I change the resolution, is this still like? Is this too small? Can you read it? It's not too small. Okay.
Good.
Okay. So we got very. So maybe this will address your question. We got very excited, like, ooh, we have this brand new fancy algorithm for such a basic problem that people have been studying since the 70s. Let's code it up. And it's a simple looking algorithm. Let's code it up and show how much better it is than the Morse algorithm. Okay, so so the blue dots are the Morse counter, and the orange dots are our new algorithm. Okay, and so we ran each one like 5,000 times with did a random experiment and just plotted the empirical CDF of the error, and they are basically as you can see, performing almost identically. Okay, so then we're like, okay, well, what does that mean? It probably means the Morse counter was better than we thought. Okay, like it already achieves the same bound. So how can we prove that the Morse counter achieves the same bound? So we went back to the Morse counter and we reanalyzed it, and it turns out that the analysis of this also conceptually is not very difficult either. There's some calculations, but the idea behind the analysis is not too complicated. So Morse A is the version that increments with probability 1 over 1 plus a to the x, and the estimator is this n hat, which is an unbiased estimator. And we said to ourselves, consider running Morse for an infinite number of increments, okay? And define zi as the number of increments it takes to go from x being I to I plus 1. And of course, every time you increment n, the probability you increment x is this 1 over 1 plus a to the x, right? So how long does it take before you increment? It's a geometric distribution. So this zi follows a geometric distribution. And let me define two values of x. X is the thing I'm actually maintaining in memory in Morse. X low and x high. And basically, without looking at the math, the way I define x low and x high are such that as long as the final x lands between x low and x high, that's guaranteed to give a 1 plus epsilon approximation. So I kind of want to make sure that with high probability, the final value of x, at time, remember, I'm running it for an infinite number of increments. So let's label time by how many increments have passed so far. So my question is, at time n, where is x? Is it between x low and x high? And if so, I'm happy. Okay. Yeah, so good. So it's equivalent to say that I'm happy, I have a good approximation if this particular prefix sum of the zi's is at most n, and the prefix sum that goes to x high is bigger than n. If those two things happen, I'm happy because it means I'm going to land in between. And now you can do a standard, Chernoff type argument. What's the probability that the sum of the zi's is large? Do some kind of MGF type argument. What's the probability that some of the zi's is small? And then you do some calculations. Another thing which was pointed out to us after we did this and put our paper online, Eric Price pointed out, actually geometric random variables are what's called sub-gamma. And the sum of sub-gamma random variables is also sub-gamma. And it just kind of, via some standard reasoning of sub-gamma random variables, you get that concentration pretty quickly. So that's all. The punchline is that the failure probability ends up being this, e to the minus epsilon squared over a, roughly. So it basically just tells you how to set a. There's a catch. In our analysis, our analysis only works if the number of increments is large. It has to be at least 1 over a. So there's a simple fix to that, which actually modifies the Morse counter. And this is not just an artifact of our analysis. You can show that this is the truth about how it actually behaves. You really do need n to be bigger than 1 over a for the analysis to hold. But there's a simple fix, which is a one-line change to the Morse counter, which is, look, you know what your target memory budget is. It's log n plus log 1 over epsilon plus log 1 over delta. That's your target memory budget. So until you hit that memory budget, just maintain the counter deterministically, right? And then once you start to use a lot of memory, then you switch to this probabilistic increment. That's it. So that version of Morse with that one-line change, where you're deterministic in the prefix, is optimal. Okay.
So you would just reset, rescale.
Yes, I think something like this. Yes, because you haven't been using the correct p up until that point. I think you could also just imagine that your probability of increment was 1 for a while. Because you are changing your probability of increment. You don't even have to rescale. Your probability of increment is changing as x increases, right? So you can just say in the prefix, my probability of increment is 1, and then at some point I start making it not 1. Okay, and the lower bound, I know we started slightly over, so how much time do I have? 5 minutes. 5 minutes. Okay. So the lower bound. So good. Fix epsilon and delta. Let's say you have an approximate counter, which is an epsilon delta approximation. And let's say that it uses S bits of memory. Then your memory has to be at least the min of 2 terms. One is basically this new bound that I showed you with the improved Morris counter bound. And then the min of that with log n. Obviously, so the point is, if you want delta to be super duper small, then at some point Morris is not optimal. You might as well just maintain the counter deterministically. So this is basically the best. This is the optimal lower bound that matches. Either use Morris or use a deterministic counter, whichever is better for your setting of parameters. The proof of the lower bound. So if you notice in the second term in the min, there's log n plus log 1 over epsilon. That's like one thing. And then there's log 1 over delta, which is like the part that requires actual thinking. So the first part, the part which is log n plus log 1 over epsilon, I don't know if it was written anywhere, but it's folklore. It's like a very standard kind of argument. Essentially, it's just you just ask yourself, like, how many different answers are there? Well, the value of the counter could be 1 plus epsilon, or it could be 1 plus epsilon squared, or it could be 1 plus epsilon cubed, and so forth. Each one of these essentially needs a different memory configuration. How many different powers of 1 plus epsilon are there? Okay, and so you get log of that as a lower bound. So it's something very simple. I'm going to skip it. The next is the getting the dependence on the failure probability, which is where the action actually was, and it's actually not too complicated either. Suppose the algorithm gives a 2 approximation with probability 1 minus delta. Define some parameter t. Then, because the 2 approximation, it can distinguish the case that n is less than t over 2 versus the case that it's between 2t and 4t with probability 1 minus delta. So now, for the sake of contradiction, assume your memory is much less than log t. It's much less than half log t, which is like log 1 over delta. I'm going to define a new algorithm, which is partially de-randomized, called cdet. Det stands for deterministic. It's randomized possibly in the query procedure, but I'm going to make its increment procedure deterministic. And how am I going to make its increment procedure deterministic? I'm going to look at my current memory state. I'm going to look at the algorithm C, which is the supposedly good randomized algorithm. Now that I've incremented, C has a probabilistic choice of how it's going to update its own memory state. cdet will just choose the highest probability transition and just deterministically go there. Okay, so its update is now deterministic. And because I increment only n times, or n plus 1 time, or I init once and I increment n times. So there's a total of n plus 1 update operations. The probability that C and this deterministic version of C follow the same exact transition path is, so at any given point, I only have, sorry, what do I want to say? I want to say that one of my places that I transition to has probability at least 2 to the minus s. So it's the probability that I follow the same exact transition path is at least that to the n plus 1th power. So condition on this event, the failure probability of C, the probability that they follow this, condition on the event they follow the same path, just by Bayes' rule, the probability that C fails at most 1 over this times the original failure probability. And good. If n is less than 4t, then this expression is at most a third. Okay. So what that says is this deterministic update rule has failure probability much less than 1, less than a third, which basically means it always succeeds. Okay. So this is the statement that I've shown. And now I'm going to do something which looks kind of like the pumping lemma, I guess, is it called? So I'll say, just by pigeonhole, there must exist 2 different values of n between 1 and t over 2 that cause cdet to reach the same memory state. Which means that if I look at doing n1 increments, n1 plus k times n2 minus n1 increments for any integer k, I also reach the same memory state. But one of those values has to land between 2t and 4t, which means I'm going to basically say the same thing for something in this range and this range, which is a contradiction. And I think I'm almost out of time, so let me just say the very last thing. Is this the end of the story? The original applied motivation was that I wanted to store many counters, like in Redis, not just one counter. And the total memory is basically the number of counters times the memory per counter. That's why Morse is valuable, because it decreases the memory per counter. But you could ask a question, which is, and this, we got asked this question by Greg Valiant at some point, which led us to the following work. Maybe if you look at your problem as like, what I have is actually the K counter problem. It's a different problem. Can I solve the K counter problem more efficiently than K Morse counters? Okay. Rephrased, is there a non-trivial improvement in the amortized space complexity of approximate counting that's more memory efficient than simply K Morse counters? So this is the K-fold approximate counting problem. Maintain K counters with 3 operations, set them all to 0, increment I increments the ith counter, and query I returns the ith counter. The straightforward solution would be something like K log n over K bits of memory. With K Morse counters, you would get something like that. Can we do better? And the theorem that we have with Yanjun and Ishaq and Huacheng is basically no. There's no amortized improvement. There's no improvement using amortization for the K-fold approximate counting problem. Yes?
Why there is no delta over K there instead of 1 over, like K over delta? Why don't you have to do union bound over?
Well, okay, so my definition of the problem is that for when I say query I have to return the ith counter with good probability. It's not. My definition of query is not return all the counters. But yes, if you had to do that, then you would ask that. Does that make sense? Or? Okay. There is a restriction in our theorem where we have to assume in our proof that epsilon is less than 1 over log 1 over delta. But other than that restriction, the lower bound holds for all parameter regimes, and it's unclear whether that restriction is necessary. It's just we didn't know how to prove it without that restriction. So that's still open, removing that restriction. I think am I over time now? I'm probably over time. Okay, so let me just say, I won't say the proof because I'm over time, I think. Basically now the harder part is again with the failure probability part. Basically proving a lower bound of K times log 1 over delta is the hard part. And we have a proof already when K is 1. That's the kind of pumping lemma type thing I showed you. When K is bigger than 1, normally people in the audience might have heard of like direct sum. You prove something for K equals 1, you lift it to the K-fold problem with direct sum. The problem is we didn't prove our lower bound via information complexity, so it's not clear how to do that. And we tried, we still don't know how to do it that way. So we basically had to reprove the K equals 1 theorem and prove an information complexity lower bound for K equals 1, and then lift that to general K using direct sum. So the hard part is the first part. And this is a very standard approach to proving lower bounds in this space. And I don't, okay, so and the notion of information complexity we use is maybe something interesting to point out. We don't use the typical ones that people had been using in 2002, like the external or internal information complexity. We use this one that was introduced by Braverman, Garg, and Woodruff just a few years ago, which is, I'll define, for our purposes, information complexity is this thing. So T for me is the length of the stream. Okay, I didn't go through the whole slide. And what I'll do is I'll sum up over all points in the stream. Then I'll sum over all the points leading up to that point, the prefix of that. The mutual information between the memory state immediately after processing the ith token in the stream and the jth token in the stream, conditioned on the j minus first memory state. So this double sum, Braverman, Garg, and Woodruff proved, is a lower bound on the sum of all memory state lengths. So in other words, if all the memory states have the same length, they all use s bits, the right-hand side is s times t. So you can think this information complexity is a lower bound on s times t. So the lower bound you get on s is this IC divided by t. Okay, and this notion of information complexity also satisfies some kind of direct sum. Okay, so now the game is come up with a hard distribution over inputs. This is the usual game. Show an IC lower bound for this hard distribution. And that's kind of where all the work is, and I'm out of time. So you can take a look at the paper if you want to see that. Okay, thank you.
Questions. So if we go back to your plot.
Oh, sorry, okay, I shouldn't have done.
Oh, You don't have to go. This is a question for you.
Oh, yeah.
The effect of like having to store the counter exactly for the first, long number of steps. Like that part is crucial, right? So the analysis.
It is.
You can't really see it in the plot.
I guess it's because in the plot, the number of increments we did was such that it exhausted that prefix of time. Yeah.
But if you did that, then would you see some like discrepancy between like the regular Morris and maybe?
Oh, and the new algorithm? Oh, we didn't do that experiment, so I don't want to promise anything. Yeah.
You asked this question about counting in terms of the k, the number of counters you're
Yeah,
counting.
yeah.
Does your answer change if most of the counters are 0?
You said, does the complexity change if most of the counters are 0? Most of the counters are 0 because
You're doing n grams and n is 20.
oh, like n. Oh, so n is just like much less than k. Is that the point? Because if n is much less than k, then most counters will have to be 0, right? Because you don't even have like enough increments to touch each counter once. Is that what you're? Is that the? So k is the number of counters, n is the number of increments. So if n is much less than k, then there are a lot of counters that just never got touched. So most of them have to be 0. Is that the case you're talking about?
I wasn't thinking of it that way, but let's say yes.
I mean, I think it's the case that. Well, actually, let me just look at what is the form of the lower bound. I think okay. So if I need to look back to be sure, but I think this this log n over k, because it doesn't make sense when n is less than k. So I think this might actually be like the max of log of n over k in 1 or something like that. In which case, the bound would be k, which is the right answer, I think. But let me not say with 100% certainty.
K. Yeah.
If what? Sorry.
Less than k.
Oh, less than k.
You're saying
You have a strong promise of extreme sparsity.
Oh, I see. Like for example, there is an upper bound which is simply like n log k, right? Which is just like you remember the stream. I guess maybe when I need to look back. It might be implicit, like when we phrase our result, that we just assume that n is at least k, because otherwise there is this n log k upper bound.
I don't necessarily know that n has to be less than k.
Oh, yeah, okay.
Sparse.
Or you just know that it's sparse for other reasons. Like maybe n is huge, but you just know that the increments are concentrated in a very small number of values. We didn't look at that, so I don't want to like promise anything.
The n-gram problem, you might not even care if it only appears a handful of times. You just know that the things that appear frequently are very few.
Yes.
It's important to know them.
Yeah. I don't want to promise you I don't know. Yeah. Oh yeah.
What's the situation when decrements are allowed?
Oh, when decrements are allowed, there's nothing non-trivial. For like the single counter problem, you need log n bits of memory. Any other?
Okay, thank you so much.